Hello, everyone. I think we're back online. The next speaker is Meyer from tenKsolar, and he's going to be speaking about shading losses and gains with reflectors for low-X concentrators.
Great, thank you. Can you hear me okay?
Yep, we can hear you fine.
Great. So let's go to the first page. Well, actually, yeah, second page, I guess. So I thought I'd give a very quick corporate overview for those that may not know who tenKsolar is. We're a privately held, we're in our 6th year of operation. We basically are a PV system supplier. We don't supply just modules or just racking or just inversion. We actually supply the entire system that's actually integrated together to work in a very unique way. And I'll take you through that. We're corporate headquartered in Minneapolis, Minnesota. We have manufacturing sites in Shanghai, China, and Minneapolis. We have quite a few intellectual property filings around the architecture and how things work in our system, and I'll give you a little bit of a snapshot of that. And we have installations in 18 U.S. states, Canada, Europe, and Asia. We have about 200 systems installed, about 10 megawatts of products in the field, and are expecting to somewhere between double and triple that here over the next year. So to give you if you go to the next page, to give you an overview of the tenK system, we basically we integrate electronics in a very unique way inside the module. It's actually what makes it unique, and I'll talk a little bit about the cell architecture, is we actually have 2 interconnections on every cell. We have a serial connection and a parallel connection to actually form what would, I think we have described it as kind of a mesh configuration. We do build some serial voltage from the PV system itself, but then what we do is we actually incorporate a group of redundant conversion units inside the module. There's actually 6 units inside the module. We actually only need 4 to produce full power, so we can tolerate 2 electrical failures within the module. In addition to that, cell cracks, interconnection breaks, other things have very, very little impact on our module because of the way the cells are interconnected. And what we do is we take that very unique module, and I'll talk a little bit more about that architecture in a few seconds. But what we do is we actually integrate that into a complete system where we actually have a roof, a rail that actually sits on the roof, as you can see. The modules actually have extensions on the frames that actually form the rack, so the module actually is one portion of the rack. And then we actually form the third part of the rack by a reflective element. And that's really going to be the subject of today's discussion. And that reflective element actually has a couple of characteristics. Number one is it's a product that we worked on with 3M. It's a spectroscopic based material. It's actually glass on the surface. The spectroscopic character comes from a film that's actually laminated to the backside of the glass. So from a maintenance ruggedness standpoint, it's glass on the surface. But on the backside, it's got this spectroscopic film that actually reflects only a certain band of the solar spectrum. And what makes it even a little bit more complicated is it's actually angle dependent in terms of what that bandpass is for what gets reflected versus what gets transmitted through the film. And then some other features of the system, we point to PV panel south, as you might expect, and then basically we use the reflective material, the reflector, to actually pick up the light that would normally fall in the gap between the rows, and we push that over onto the adjacent panel. What makes this all work is the unique architecture of the panel. If you try to do this with conventional, you would actually create a situation that's a little bit like partial shading. Some of the panel would see higher illumination than another part of the panel coming off the static reflector, and therefore it would feel like variable illumination, and generally you'd see bypass diodes trigger other imbalances in the panel. And so with our architecture and our module, we make that possible to actually take that reflection and reflection gain over onto the other module. So to talk a little bit about what's inside the module before we get into how we treat the rest of it from an architecture standpoint, if you go to the next page, so from a serial standpoint, I think everybody knows, and you know, if you basically have a single path through an individual module, or a single path through a group of modules by interconnecting those in serial. If you go to the next page, please. Sorry about that. Page 4. Yeah. So basically, then any disruption that happens on the photo-generated current, soil, shade, damage, anything, really has an impact on the entire system. If you go to the next page, page 6, basically what we do is, So basically what we do is we actually, as I said, we embed the electronics inside the module. We actually interconnect the cells in a combination of parallel and serial connections. And then what we do is we actually export the energy from each module to a parallel DC bus connector. And it's very low cost for us. We've engineered out a significant amount of cost on doing the architecture this way. And all the energy then flows into this parallel bus. And we don't show it on here, but what we actually do is we actually interconnect redundant inverters actually to that parallel bus that operate with a slight change to the firmware of what a typical inversion unit would operate at low voltage. And basically then we can actually take all the energy that comes off this DC bus and we can run that through any inverter that's actually connected to that bus. And so we can not only improve the efficiencies at low light because we run only the units that we need, but we can also tolerate failures in the inversion side where we have very little energy impact upon failure with that configuration as well. So energy from any module, really, if you go all the way back, energy from any cell can actually find multiple paths through the module, multiple paths through the electronics in the module, and then also multiple paths out to the grid through the inversion process. And that's one resultant part of that is the ability to accept non-uniform light. So on that, if you go to the next page, it's just basically a simple illustration that if you have static reflection, generally the static reflection only occurs over a portion of the module. It's very difficult to design a static reflector that would actually eliminate the module uniformly at all conditions through the year. And so we basically, because of the architecture of our system, we can actually gather all of that light in and actually produce that as more and actually get more energy out of that out of the system. Whereas if you had a individual serial panel, obviously that wouldn't be the case. And because it's spectroscopic, the amount of thermal increase that we take on the panels is actually relatively insignificant as well. We see a few degrees of additional heating versus if we had a full spectrum reflection element that was actually doing this work, we would see a significantly higher temperature on the cells that actually have this reflection gain. I should probably also mention that inside the module we actually have a different module stack as well. So because of that module stack, our NOCT and our basic thermal properties of the module are significantly better than what a conventional module would be as well because of the way we built the package, but I won't get into more of that here. So the purpose of this talk with that introduction is really then how we do the reflection modeling and how do we treat this from a modeling standpoint using SAM. And then following that, I'll give a brief overview of actually some data that we've collected through Chris Delaney's group at NREL. We've got a reference system operating there that's been there for just about a year and a half. So if you go to maybe skip 2 slides, you can skip the reflection modeling. Yes, so stay on this slide for a second. So basically the reflection gain, the way we treat that is basically as an integral that basically takes the reflection element and we actually go through a vector analysis to determine how many of the individual vectors will actually end up resulting on the PV module. And so we actually accumulate all of those, and I'll go to the table next that actually shows how we do this in SAM. But we actually use the altitude by azimuth table to actually take that, essentially that integral in terms of the reflection gain, taking into account the properties of the reflector as well. And we actually use the altitude by azimuth table to actually build a table that instead of having all the elements be less than 1, we actually have a group of elements that's actually greater than 1 that basically tie back to the overall performance of the system. The other thing that we actually overlay on top of that is actually the Fresnel losses that we take on the surface of the PV module. And then we actually haven't done this yet in the model, but also taking into account the Fresnel losses that result from the incident angle from the reflector onto the module as well. We have not embedded that into the table that you're about to see, but we have. So now, if you go to the next page, this is just an example of the altitude by azimuth table and the granularity that we typically use as shown, where we basically take and we do the calculation of what the energy gain is for a particular sun angle, both azimuthly as well as height-wise for the angle coming in, and then we basically form these reflection coefficients then that basically get incorporated into SAM as we do the individual runs. As an example here, the reflector gain value of 1.13 happens to be at the particular condition shown, and you can see how those values vary. Again, there's actually a Fresnel loss that's actually incorporated into this as well, albeit the Fresnel loss is a relatively small number in comparison to the reflection gain table. We also, on the diffuse, we actually use a sky view analysis to actually calculate the diffuse effect of the reflector as well, and we incorporate that into the model as well. So we effectively then to model actually a reflected module inside the array. It's really a combination of two things. Number one is we use the altitude by azimuth table, and then also we use a diffuse reflection gain value to actually fully embed the effects of reflection into SAM. And so if we want to look at a module that does not have reflection, we basically can turn those off where we only use the Fresnel direct loss off the module. And then when we turn those on, we can actually, by using the exact same module characteristics, we can actually then predict what the changes are from the incorporation of the reflector. And I'll show you some data that we've collected here in a bit, actually coming up. So now if you go to the next skip forward one, you go to the NREL model validation. So if you look at the, we've got, this is actually a system generation that's actually a generation older than what we're delivering today. This is what we call the Neptune Panel. This array has been at NREL for about a year and a half in Chris Elaine's group, which was when it was set up. I think it was set up in March of a year ago, February, sorry, and it's been operating ever since. And the system has basically instrumented the DC bus and the inversion technologies incorporated into the system, but it's also got a separate set of measurement devices on it for both module temperature, power output, and other features. I should also note that the modules actually collect and report all the power information and report that through Powerline as well, although that's not enabled on this system. We're actually using independent measurements. And then we've got a number of optical tools for reflection and also thermal measurements to characterize the environment. So that's shown on the next page. I apologize, page 13. So we've got both the direct measurements that are actually occurring on the module, and then we also use the NREL weather system for comparisons as well. So we've got a reference paper if anyone's interested, but basically what we've been able to do, if you go to the next page, page 14, sorry, is by actually putting in the parameters of the module and building the parameters of the module, which are quite unique from what a conventional module would be, and I don't want to go through that here, but what we've been able to do is actually build a model that basically models the non-reflected modules, and we can get within about 1% on an hourly correlation. We can get within about a 1% predictability using SAM for the non-reflected module. And then what we can do is we can actually, just by turning on the altitude by azimuth table modifications I went through earlier, as well as the diffuse factor modification, we can actually then model within 1% the reflected values that we measure as well. And by not having to change any of the other module parameters, that gives us a very high degree of confidence in the approach and the results that we're getting. Just to give you an idea of what that comparison looks like for the system, this is an example of basically the energy yield on an hourly basis versus the plane of array detector that's actually on the system in kilowatt hours per meter squared. And what's shown on here is actually the reflected row, which is the black information, or the black dots. And then on there is also a yellow and a red. The yellow is actually the non-reflected row of our system, and then the red is actually, I'm sorry, make sure I get these right. The red is actually the non-reflected row of our system, and the yellow is actually a conventional array operating at 40 degrees of tilt. And the reason we have these broken out by month is the reflector actually has a very significant impact from the months of April through about October in the the latitude that Golden is at. And then in the wintertime, actually, we have actually packed the system together so we get some in-a-row shading, and the reflector is basically inactive. And so if you go to the next page, there's another example month of June of 2012. You can still see the very significant offset between the reflected and non-reflected rows. And then if you go to the next page, shows October, where you can see actually the reflector is basically becoming inactive. At that point, you can still see some gain for that, but you can see it's dropping off. And then in November, if you go to the next page, we show November of 2012. And you can see actually the reflector values are gone. If we had a December we didn't include in here, or a January, you would actually see the reflected rows being slightly below the conventional system and the front rows of the array. So that, from an overall, as I mentioned earlier, from an overall confidence level in our predictability for both the non-reflected and the reflected rows, we feel highly confident in our capabilities using the SAM model. So the last thing I just wanted to mention, if you go to one more page, let's see, 18, is basically this is the most recent release that we've had a 10K for the product. It's the same architecture as what I went through previously, same architecture as what's operating at NREL. However, it's a larger module. We call it the RAISE XT. It's a 410-watt module, a 96-cell equivalent. We've got two configurations where we actually change the packing density of the array. We have what we call the XT26, which is a higher density, both power and energy, for maximum rooftop production. And then we have an XT28, which is optimized for additional energy production per watt, where we sacrifice a little bit of the energy density off the system. So, and that product's in general availability now as well. So if you go to the last couple of charts here, page 19, this is just an example of a SAM comparison where we take the weather file, we feed that back into SAM, and that compares to what an actual snapshot of one of our RAISE XT26 modules is actually producing. This is a DC comparison here, where we're looking at 3.36 kilowatt hours DC on versus 3.25. So you can see that from a predictability standpoint, we're quite good there as well. And then the last two pages is basically, if you go to page 20, is just a comparison of the modeled energy yield in terms of performance, comparing it to a conventional system, and then also comparing the two RAISE configurations that I mentioned earlier. You can see the energy yield is significantly higher through those the time periods shown. And then if you go to page 21, is basically the cost of energy. One thing I did not mention was the cost of the technology in the product. I think a lot of times when you talk about redundancy, people think that it generally is higher cost. What we've really engineered from an overall cost standpoint is we've been able to actually, because we could actually simplify the module with the interconnectivity and some of the materials we use, we actually have been able to get the module cost down to a point where it's very competitive with a conventional module. And the way we've actually architected the DC bus, the wiring, and then the inversion, we're actually quite competitive, and the racking, we're actually quite competitive on the balance of systems as well. So we can sell a system that's actually competitively priced, very, very competitively priced, that puts out more energy and it has full redundancy built throughout to eliminate single points of failure. And, you know, the reflection gain and the capabilities that we have with this is obviously part of that overall package. So I think we're probably out of time, so I'm going to stop there. If we could, we'll go open then for questions.
Thank you very much, Dallas. Do we have some questions on the phone?
Again, if you would like to ask a question, it is *1 and record your name. I'm showing no phone questions.
Okay.
Oh, sorry, we have one phone question here. Eric?
Yeah, can you tell us a little bit more about the electronics that are in the panel?
Yeah, so what actually resides in the panel is actually a set of low voltage DC to DC conversion units that actually have we actually use a low impedance ground plane that actually takes out a lot of the parasitic of the module, but also gives us a very tight voltage control point. And we actually, through some sense algorithms and some other things in firmware, we can actually determine something about the current flow through the panel and actually optimize the module through the impedance of these parallel circuits, actually by using some of the control capabilities between them to actually optimize the energy flow off the module at a much more granular level than you could with a bulk DC to DC optimizer on that's typically used in the industry to date. And hopefully that helps. It's a little, some of our IP architecture is kind of tied up in how we do that control. So.
Sir, we do have a question on the phone.
Hello.
James Morley, your line is open.
Hi, can you guys hear me?
Yep.
Okay, great. Thanks for the presentation. Just had a question. Is your the reflector the table for the azimuth and altitude correction for the reflector, is that now incorporated into SAM? Or is that something that we need to just independently retrieve from you guys when we want to model this?
Yeah, you would actually get it from us. We would send you an input deck.
Yeah, in the next slide. If you go to the next slide, that link has a link to the presentation will gives you more links, unfortunately, but you'll get to the files that have all that information in there.
Okay, thank you.
So if you want to look at it, you can just use that.
I have no other questions on the phone at this time.
Well, if there's no other questions, we will thank Dallas again for this excellent presentation.